All right, next one is going to be Chris Down is going to be talking to us about Linux memory management at scale.
Hello there, you lovely people. Hope you've had a good lunch. I'm Chris Down. I work at Facebook on the kernel team. I mostly work on improving memory management within the Linux kernel. I'm also a maintainer of the systemd project, so you can heckle me later. Mostly I spend time thinking about how we can make Linux more reliable and usable at scale. And that kind of feeds into what I want to talk about today. I want to help you get more of the tools and information that you need to manage memory at scale. There are many misconceptions among even senior engineers about the primitives that we provide around memory in the kernel and what they are good and what they are not good for. Memory management in general is a really inexact science where basically everything is a trade-off. So I want to help try and give you some information that might help you make the right trade-offs for your services and your workloads. Hopefully you'll come out of this talk with a little bit better understanding of how you might be able to make your memory management more efficient for your specific case. So here's a talk within a talk. First, before we go into that, how about we go back to 2017. I came here at this containers dev room with exactly the same people running it, although this one is from KubeCon. And I gave a talk about a thing called cgroup v2. Cgroup v2 has been, for the last few years, our big bet for resource control and management. And cgroups are a kernel mechanism that we're essentially building to balance and limit things like memory, CPU, I/O, some shared resource which you have across a machine. We have pretty good problems at Facebook and as an industry as a whole. Our user base is increasing, more people are on the internet, our product range is diversifying, but with that growth comes scaling problems that we've never really had to deal with as an industry before. And in the next few years, especially at Facebook, we're going to feel this massive crunch for capacity. And we simply can't solve this problem by throwing more and more computers at the problem or more RAM at the problem. We have hundreds of thousands of machines. Any small loss in one of those machines represents a huge absolute loss in resources for the company. So we need to use more resources more efficiently, and cgroups are a huge part of that. It's also really important because a lot of huge site incidents and outages, not just for Facebook, but for people like Google, LinkedIn, all the big sites, are caused by lacking resource control. Not being able to readily control things like memory, CPU, I/O can either cause problems or it can make existing problems significantly worse or longer. So resource control issues, of course, some of the most pervasive problems in our industry, and we need to start an initiative industry-wide to solve this, and that's largely why cgroups exist. 2 years ago, it was kind of, well, I think we're in Europe, so this is an appropriate thing to show, but 2 years ago, it was a totally different story, though, right? We really only had one user of cgroup v2, which was us. Like, not even Google was using it, and they like to use everything. But we were really the only people using it. We had a bunch of different primitives that we had just found out about and were using and invented. But when we actually came to use them, it kind of went a little bit like this. It's not completely wrong. Like, what we got is like somewhat there. But we got to work out in what cases do we want to make the primitives a little bit more round, and in what cases do we want to make the operating system, a little bit more square. So finding the right trade-off takes a lot of production experience and a lot of production experimentation. Another problem is that cgroups, literally one of their jobs is to limit resources artificially within the machine. And one of the things that happens is that can cause another resource to then become oversubscribed as a result. For example, if you artificially limit memory, say you limit something very tightly, an application that should use 1 GB and you put it in, say, 200 megabytes, all that's going to happen is you start hitting the disk a lot, because you're going to start to have to swap things out. Even if you don't use swap, you're going to have to end up taking stuff out of the page cache, so you're going to end up hitting the disk more often to do these things. So you end up just with essentially the shittiest memory that money can buy in the form of a disk. So as such, we need an underlying operating system that mitigates these problems and allows us to limit these things without affecting other parts of the system. This is also why, in a talk about memory, you'll hear me talking a lot about I/O in this talk. Disk I/O is something you really need to have control over if you're going to limit memory. Without I/O control, memory control is really just an academic concept. It doesn't, if it's an effective memory control and you don't have any I/O control at all, you're just going to destroy the machine. And the existing solutions we have in I/O control, in memory control, which don't affect I/O, it's mostly because they don't work. Another problem is that while we've had cgroup v2 kind of academically working like this for a while, for the past few years, a major focus has been issues that it brought up elsewhere in the kernel. because Secret v2 actively limits things effectively in a way that we've never really had before, it's brought up a lot of issues in the kernel and limitations that we've had to either fix or work around. There's not really enough time in these 30 minutes to go over the cases that we've had, but if you're interested, I do go into them in detail in my talk at SRECon from last year. We found and fixed issues all across the kernel, from kind of the IO stack to file systems to memory, just to make this work and make resource control not break down under scrutiny. And a huge amount of our time has been invested in that kind of stuff. So how about we kick off kind of the main part of the talk now? I've got all the disclaimers out the way, by discussing some of the fundamentals of Linux memory management. So these are pretty important to go over, even though some of you may already know most of this, because if we don't agree about this, then the whole rest of the talk is going to absolutely be completely useless. So one thing that's really critical to understanding Linux memory management is that Linux has these different types of memory. From the CPU's perspective, there's really not much difference. It knows a little bit, maybe. It knows something about permissions. It knows something in the MMU. But it doesn't really know what the semantic intent of your memory is. For example, for Linux, anonymous memory is, as the name would imply, memory which has no backing storage. It has no name, usually things which you allocate with malloc or mmap, map anonymous, stuff like that. Most people also know about cache and buffers, two sides of the same coin, but if you ask most Linux users what they think about like buffers and caches, they will say it's reclaimable. And I'm sure most of you would agree with that, but the problem is most people's understanding of what reclaimable means is a little bit off. It doesn't mean that you can reclaim it right now. It means that you might be able to reclaim it, if you ask nicely, in about 5 minutes maybe. For example, if some application is like hammering the shit out of some file, we're very unlikely to evict that from the cache. And the kernel knows this. It's not going to keep on evicting that from the cache when your system won't be able to make any forward progress. This can cause some confusion when people inevitably ask, and do ask a lot, why did my system run out of memory when I got so much free memory available? And the answer is, well, you know, it's not actually free. These things do serve a purpose, and we can't always trivially free them. So we'll come back to more of these kind of cases which are non-intuitive in a moment. The fact that caches can be essential is another example of why RSS, the resident set size, a metric that we love to measure, is pretty much bullshit. And we measure RSS because it's really easy to measure, not because it represents anything useful, which is just fucking, I don't know what the fuck that's about, but as an industry we got to stop this shit. RSS often skews a lot of attention to very, very specific types of memory. It skews a lot of it to file map memory and anonymous memory. We forget, though, that many workloads simply cannot operate without these disk caches, without these page caches. And if you take them away, they wouldn't be able to run. In one case inside Facebook, a team which for years had thought that their operating footprint was like 100 to 200 megabytes, discovered through the metrics which I'm introducing in this talk that the actual footprint was on the order of more like 2 gigabytes. And this is one of the reasons why RSS as a metric just doesn't make a whole lot of sense. So this brings us somewhat neatly onto swap, a completely uncontroversial topic which no one has any strong opinions on. Swap is really widely misunderstood. A lot of people think that swap is kind of pretty much irrelevant nowadays with gigabytes of memory. But this is kind of a strange opinion because swap still does a lot of good stuff, and most of the things that it does well, you really can't get them any other way. And for the stuff which it does poorly, and it does do some stuff poorly, you can mitigate it, like there are ways to get around that. Usually these discussions kind of hinge on misunderstandings about swap is actually for. Using swap is almost all about promoting this positive memory pressure, using as much memory as possible, and it almost has absolutely nothing at all to do with being a slower RAM or like emergency memory, which is what people tend to codify it as. People also have this really, really strange idea that if you run without swap, when you encounter memory contention, disk IOs don't happen. I don't know how people got this idea, but obviously that's not true, right? We have to evict something, and what we're going to evict is really hot page cache pages. So you're going to end up hitting the disk for those instead. You just end up making the reclaim less efficient. Even worse, like, we end up reclaiming things which we otherwise wouldn't want to reclaim. You're reducing the amount of things which we can reclaim. So these kind of misunderstandings have really hobbled swap's reputation and led to this belief that it's not useful in 2020, which is not really true. So if swap isn't a mechanism to expand your RAM, then what is it? Well, swap allows reclaim on types of memory which otherwise would be locked in memory. That is, it provides the backing store for things like anonymous memory, where we simply don't have anywhere else to really store them except for physical RAM. Without swap, it's really, really hard to run hot on memory. It's hard to run memory-bound workloads because we almost immediately go from this state of the system being totally fine, running at the maximum capacity, to, oops, you've gone one page over and now the system is kind of in the ground. And that's not really how anyone wants to run a system. Another thing is that if you've been compiling things, you've probably seen like this make j cores plus 1 stuff. It's pretty much what everyone compiles like. Why do we run with cores plus run? Why don't we run with cores? Well, the reason is because we want to promote a little bit of positive pressure, right? In case one of the threads starts doing a little bit less, we want to make sure that the cores are being totally utilized all the time. And swap allows us to do the same thing with memory. This comes back to kind of what I was saying about, as the operating system, we want to make the most efficient use of memory possible. And we want to do this without impacting system latency too much, which is kind of impossible if you don't have swap. Without swap, these memory contention increases happen really, really suddenly. And often, there's no way for your system to recover from that state. That is, when we go over the edge, we go really over the edge. And often, your system can enter some pathological outcome as a result. Swap does come with some trade-offs. I mentioned there was kind of some downsides. This is a really, really long post. If you're of the perception that swap is not useful, I really recommend reading it. And feel free to send me an email or whatever if you have some comments. One reason why people don't like swap is because they think the killer will come to their rescue. The killer is the out-of-memory, it handles out-of-memory situations in Linux, and it's essentially a massive, massive fucking cannon that you point in the direction of some process, and you pray that it was facing the right way. And usually, it was kind of facing up instead of down or some bullshit like this. It really doesn't really do what it says on the tin. Usually if you're running a web server, for example, well, the web server itself is like the largest thing on the system, so it will just kill the web server. Fucking genius. However, the killer kind of has this constraint, right? Like, one is, when you use it, you've pretty much already lost. Usually by the point that killer is invoked, all of your applications on the system have kind of become queued up to hell. And this is because, due to the fact that memory hotness is hidden behind the CPU's memory management unit, we actually have no fucking idea when you're out of memory, right? Like, this is not a Linux thing. This is the same for basically every modern operating system and every modern CPU and every modern memory management unit. We have no clue when we're out of memory. This might come to a shock, as a shock to you, but the reality is we just have to eventually work out that we didn't get pages for a while, and probably that means we're out of memory. Generally, as I said, only the CPU's memory management unit propagates this information, which means we have to poll for it. We have to walk the page tables to find out if this thing actually is hot or not. And so we have to periodically poll, which is really, really expensive. So we can only do it when we're already doing reclaim. So the problem here isn't really knowing when our memory is full, because that is the state we want to be in most of the time. But what we want to know is not what's resident, but what we could take out of memory if we had to, and that's something which is hard to know ahead of time. As you'd imagine as well, we only really want to invoke the killer when we really are out of memory. This means that there can be a really, really long delay from you running out of memory to the killer actually being invoked. So we have to already go through a lot of reclaim attempts, already through a lot of iterations for the system to finally decide we're out of memory and I should actually kill something. So relying on the killer to do this reliably, just because you don't have swap, is really not true. And I'll show some graphs at the end to show that. Our goal in general should be to avoid to invoke the killer at all. And I'll go over how we achieve that in a slide or two. The second problem with the killer is that it's not really configurable. We have this amazing proc file called score and score ADJ for score adjust. I love anything in the kernel which is called a score because it means nobody knows what the fuck the numbers mean. And this is kind of true. Like, you kind of set it to like 1,000 or like -1,000 or like some value, and you pray that it's bigger or lower or something than another one, but you really don't know like how the killer will react or what it will kill. So it often results in the killer completely killing the wrong thing, and then kind of only eventually randomly getting the real thing which is causing the problem on the system. So I mentioned this whole Unkiller shenanigans works based on reclaim. Well, how does reclaim work? So reclaim is this process of trying to free pages. There are multiple different ways reclaim can happen. Two common ways are this kswapd reclaim, and another one is called direct reclaim. Kswapd reclaim is done in a background kernel thread. It's kind of not in any part of the application lifecycle, and essentially we're trying to proactively free memory when we go over some threshold of used memory on the system. This happens, impressive. This happens passively when you're past, say, 97% or whatever of your memory, and we try and prune it back down a bit. Having this happen prevents going into this next and kind of scary phase of reclaim called direct reclaim. Direct reclaim requires suspending the application which is requesting memory, which is really bad for latency because we've now tried to request and there's no free pages available. So your application has to wait and be suspended while we try and go get some. This can result in your services having actually measurable freezes. Or if you're an Android user, you click buy now and your whole phone freezes. That's not a good experience, right? So we want to avoid that where possible, and that's what the kswapd thread is for. Reclaiming some pages may also be easier or harder than others. So when we talk about reclaimable memory, like I mentioned, some page types may be reclaimable, just not quite right now. For example, some cache pages may be so hot that we don't want to evict them because we know the system performance will tank. The same goes for anonymous pages, which if you have no swap free, they have no place to go, so they're essentially locked in memory unless the application itself does something about them. Some page types might also be reclaimable right now, but we can't just reclaim them. We have to do something else. For example, if you have dirty pages, we have to flush out the modified data to the disk before we can reliably reclaim the page. Otherwise, we'd lose the modifications in the kernel, and then we would kind of have data loss, which is not great. So sometimes it's not as easy as just reclaiming pages. It kind of gets a little bit complicated. In practice, this variance and unpredictability in reclaiming is typically really hard to tell ahead of time that we are running out of physical memory. But if we wanted to know now, how would we go about it? If I were to ask you if your machine was overloaded, typically the kind of things, depending on your level of seniority and experience with Linux, you would say to look at are the most basic one is free memory. But free memory is kind of a lie because we don't really know how much of that we can take away. We don't know how much of that we could reclaim. The same goes for the slightly more correct but also incorrect mem available in proc VM info. Because that is kind of basically an estimation just based on page type. If you're a bit more senior, you might talk about something like page scans. The problem with page scanning, which is how often we're iterating to try and free pages, is you can't really distinguish from some pathological behavior where the system is about to fall over from fairly efficient use of the system. If you are efficiently using the memory on the system, you will also have a really high page scan number. So it's really hard to tell what the outcome of that is. But usually all of these metrics we come up with are just approximations of memory pressure. So what is memory pressure? What do we really mean by that? Well, we've never really had a metric like this in the kernel before. We have many related metrics, like the ones I've just gone over, but even with all of these, it's really hard to tell real pressure from efficient use of the system. So PSI uses metrics which are specific to a particular resource to tell you if that resource is becoming oversubscribed. For example, in memory, we use the amount of time which we were stuck doing this pure memory work to work out, for example, if I had more memory, I could probably have done 0.21% more work in the last 10 seconds. And this is a lot more easy to reason about than something like page scans or whatever, because it tells us this thing is actively becoming the bottleneck for the system. Mostly, these kind of things tend to be things like refaulting, doing I/O as a result of having to refault pages which we've just paged out because the system is churning over and over again. But it's not only for memory, we also have it for CPU and for I/O as well. And these can also be really useful to you in developing high reliability and high availability applications. For example, if you want to know in advance whether your system is about to run out of memory and you might want to do load shedding or blocking new requests from coming in, without having to pause the process of pause the progress of your application entirely. So it can be really useful to do that. And you can't just do this by looking at free memory or page scans or stuff like that. These PSI metrics are also what powers our pre-UM detection. We do this as part of a project which we've open sourced called UMD. oomd is a user space killer with a really fine-grained policy engine, so no more of this kind of scores stuff. This allows you to encode policies about what to do in certain situations. For example, we run chef on our machines to ensure that we have an up-to-date system. But while chef is important, if my web server is tanking because we are running out of system-wide memory, I am okay if we don't run chef for like 5 minutes. That's fine. That's not going to really be a problem. And the same goes for other background work which isn't in the critical path. So oomd allows you to encode these kind of rules about what to do based on these pressure metrics. For example, we can monitor a best effort application's memory pressure, and if it starts to cause contention for others on the machine, we can dial it back or kill it completely before performance degrades elsewhere. And using these metrics, we can prevent and avoid invoking the killer entirely, and we have a lot more reliable behavior of the system when the system is at the peak of memory. Another thing which you'll have seen me talking about if you saw my early SecretV2 talks was our limits. That's this memory.high and memory.max stuff. Our initial proposal for SecretV2 was to limit non-essential work on the machine, but this has a few fairly fundamental problems. One is that you have some applications which have really highly variable resource usage. And sometimes that's okay. Sometimes those applications do, genuinely, for some genuine reason, have variable resource usage. But it's hard to set a limit for those because if you set it too high, most of the time the application is essentially unprotected. And if you set it too low, once the memory spikes, you'll end up killing the application. So it's really hard to work out what to do there. Another similar problem is that the resource usage of some processes is really heavily tied to some other process on the machine. For example, if you have an application which has a dedicated cache, say it's like something which does service lookups, and it has a cache of the lookups it's done recently, how much memory it uses is probably a factor of what it was actually asked to do by something else on the machine. It's kind of hard for those service owners who own a service which is so dependent on another process on the machine to reason about how much memory should my application use. What people really know is how much memory does the thing which I want to run on the server use? How much memory does a web server need? How much memory does a database need? Those are things we know. We don't really know how much does this service lookup daemon need if I do this query and so on and so forth. So for that reason, we've been moving more and more towards these protections. That's this memory.low and memory.min stuff. Usually, these are kind of more uniform and a little bit more static. The way these work is that you define a threshold, say like 28G. Say you want to protect 28G for your main workload. So say HHVM, our web server, needs that much memory. You set memory.low in there, and we will, if HFM requests it, aggressively take memory away from other things on the system until HHVM gets that amount of memory. We don't prohibit other applications from using it. It's not a hard reservation. But if it turned out that HFVM does start to need them, we will aggressively start to give it back memory from other people. And this allows significantly more work conservation. Daemons can use as much memory as they like as long as they don't intrude on the needs of the main workload which is running on the system. So this is all well and good. I've gone through a whole lot of primitives. But how do we actually intend to use them to build a coherent system? Well, this is where this fbtax2 asterisk, we don't really know what we're going to call it. This is where fbtax2 comes in. fbtax2 is our overall project for resource control at Facebook. SecretV2 is certainly one of the things which we need to do that, but it needs to come with an operating system which supports its goals, right? One concern in fbtax2 is to stop background services that the main workload doesn't rely on from affecting the workload running. For example, if metric collection or chef go crazy, we want to make sure that we have them dialed back and we can deal with that. We also want to have reasonable behavior if we start to exceed the capacities of the host. I mentioned we want to run as hot on memory as possible, right? So that comes with the risk of going over the edge, of going a little bit too far and taking too much memory. So we need to have reliable behavior when we do that. It's also really important that we keep our efforts usable and lightweight. It's no good if I can now give you 10% more ability to load your machine if our solution also takes 10% of load to do that. And it's also no good if I produce a technically amazing solution, but nobody wants to use it because it's garbage. So I think these are the main three things we've got to think about when implementing a system. So fbtax2 comprises this wide range of solutions to compose a usable system. We do need to be opinionated about the base OS and make sure it's capable of isolating resources. If we're not sure about that, we might actually end up with a worse situation than the one we started out with. We also have this early killer, oomd, running on fbtax2 machines. On these machines, it monitors for threats to the workload and prevents misbehaving workloads from affecting each other or the rest of the machine. And it also prevents obviously misbehaving system applications from affecting the performance of the main thing which is running. So let's take a look at how this actually looks at the base OS layer. So we use Btrfs as the root file system. This is needed because, as mentioned in the SREcon talk, which we didn't quite go over, ext4 has some fairly insurmountable priority inversions. And the Btrfs developers have been very receptive to fixing these. It's not a coincidence that a lot of them work at Facebook. But we had a lot of problems getting these fixed in ext4. So that's one of the reasons why we run with Btrfs. I also mentioned earlier about the importance of swap. Usually we do disable swapping on the main workload on the machine, but it really kind of depends on what it does. If it can tolerate it, then it's reasonable to have it on as well. We do need swap to make sure that we're efficiently able to reclaim all types of memory, not only page caches. We're also opinionated about some kernel tunables. A big one is write-back throttling, also known as WBT. A lot of you probably used Desert Linux in like the early 2000s, right? Do you remember the situation when you would plug a USB drive in, copy some stuff over, and like your whole system would grind to a halt? Yeah, I think we all went through that, right? And that's a result of write-back. Write-back is a kind of I/O which you can't really slow down. So what happens when you're doing that is like this I/O becomes the most critical thing on the system, blocking everything else from operating. So write-back throttling is something that enables stopping those I/Os before they even go in progress. C-groups are the bread and butter of resource control. As such, it also makes sense to go into our default choices in terms of configuration there. So to get sensible resource control, it's important to have clearly defined roles from the top level so that you can delegate resources effectively. For example, we have system.slice, which is a C-group for best effort services, things which are nice to have, but which we could dial back at any moment if the machine needs it. We also have hostcritical.slice. These are things which the host needs to operate, also things which we might need if we need to go and debug something in an emergency, even if the machine is overall unhealthy. And then we have workload.slice. Workload.slice is where the main thing which you're running on the machine lives, for example, HHVM for a web server, and it's the thing we really want to prioritize the running of on this machine. This is actually how this used to look. You might notice this memory.high and memory.max stuff is back here. So we're only punitively limiting work. However, this is fairly brittle. Like system.slice memory could legitimately spike at any point. And we might end up slowing down or killing things in system.slice, even when we didn't really need to, even when the workload didn't need that. It's also really absolute. It doesn't allow ballparking any configuration. You say like, you don't say, well, my thing needs about 4 gigabytes of memory to run. You say, my thing needs 4 gigabytes of memory to run or I die. That's not usually how anyone wants to live their life, right? I mean, you need to be able to have some wiggle room and some amount of configurability there. So this is why we've changed towards using protections instead of these artificial limits. So that's this memory.low and memory.min stuff. This is kind of a guarantee that we have this memory available for the system. We don't prohibit others from using it, but if the workload were to then need that memory, we will aggressively take it away from others. You'll also notice the addition of IO.latency. I didn't really have time to go into it in this talk, but I mentioned you need IO control as a corollary to memory control. If you don't have it, your memory will just turn into IO, and then the whole system kind of just grinds to a halt. So having these completion latency guarantees, write-back throttling, and UMD kind of prevents these bad applications from overrunning the machine. As the final thing, I mentioned I wanted to talk about production success stories. In this case, this is a little bit of a scary graph, but I'll go over it with you. This purple line is without FBTax, and the green line is with FBTax. The essential point is this. With a normal OS setup, with no swap and just using the killer, the system stops working for literally like on the order of 20 minutes. This is not even like a weird or strange, this is just a web server. With FBTax 2, we actually launch a leak, a memory leak, repeatedly, and the system is not affected at all. What we're doing here is launching this memory leak inside system.slice repeatedly and trying to get it to take down the main workload, but it cannot do so because UMD just keeps on killing it over and over based on the pressure metrics. In the other case, the killer thinks the system is making forward progress because it is killing something, but it's killing the wrong things repeatedly. And even with using score adjust, this thing doesn't really get any better. One thing I'm pretty excited about is that the tools and techniques in this talk are things that we've never really had in Linux or Unix before. And I'm hoping that some people in the audience here will be able to build some of the container engine stuff and some of the process management stuff which we need based on them. This is one of the first places where we've presented this work cohesively like this. So I'm really looking forward to seeing what we can build in the future based on these. I've been Chris Down, and this has been Linux Memory Management at Scale.